Hello, my name is Dominic Mano. I am a research scientist at Los Alamos National Laboratory in our high-performance computing design group. My main focus is on storage research. Today we'll be talking about streamlining scientific workflows, how computational storage can be leveraged to improve upon these scientific workflows in HPC. Before I begin, briefly just want to thank the SNIA committee for hosting this event and having me as a speaker. All right, let's jump right in. All right, so a brief, highly summarized view of the workflows that we may see at LANL. A scientist needs to understand certain phenomena with a particular part or a particular weapon, so they dismantle it. Then they design experiments to help understand this component and any future components. So what they do is they collect physical properties of materials, they make drawings, and they identify variables of interest, which all become input to a physics simulations, which will obey all of these inputs. Now, as they move on to the computation workflow, so because these simulations become quite complex, they can take a while to run. So think many, many months, 3 months probably a minimum, on thousands of compute nodes, sometimes tens of thousands of compute nodes. And so as we all know, computer components fail, especially in a clustered environment, whether it be software hiccups, DIMM errors, power blips. And so when these events happen, we don't want to start a simulation back from time step 0 every single time because these things are time consuming. So if we encounter an error, it'd be nice to start from a known good point that isn't time step 0. So in order to achieve this, scientists will periodically save state just in case they need to restart. And then they can restart from that known good state that was saved. The checkpoints are typically 80% of memory that the simulation is consuming at the point in time. So these can be upwards of petabytes in size, often terabytes in size on the low end. Okay, so checkpoints are also valuable for another reason. So we talked about the restartability, but also it gives the scientists an opportunity to take a peek at the current state of the simulation as it's running. So they can go in and tweak certain variables or smooth out certain properties and then continue on from that specific point. And then finally, at the end of the simulation, they will use visualization tools that allow them to analyze the results. This analysis can be quite resource heavy, both time and compute. Basically, what happens is the data sets are, again, on the order of petabytes in size. And in order to find the properties of interest, and we'll look at a few examples of some things that are looked at here in a bit, but the scientists will often sort on a field of interest. So something like energy or temperature. And again, remember, there's 10,000 compute nodes. There can be millions of data points for a particular field of interest. And they're going to run these large sorts. And then they're going to run a sort on the next column of interest or a next row of interest. So these things can be very time consuming and resource intensive. Thus, we want to improve that. All right, so our first topic of exploration is going to be data management for these simulations. If we look at a quick diagram of what our current generation of supercomputer looks like, Crossroads was installed in 2023. You can see that the system used for the simulation has about a petabyte of memory. So again, about 80% of that is generally used for a single time step checkpoint. And then connected over a high-speed network, in this case it is a slingshot network, we see that we've got about 10x memory for an all-flash based luster file system. And then below that, we've got a warmer tier called campaign storage. So this is highly protected data that is stored on hard drives. 2 tiers of erasure are implemented to protect those data sets. Data sets typically live in the hot or the flash tier for weeks, maybe months. And then the campaign storage tier is definitely months, up to years if that data is being highly processed. And then finally, you want to pare down the data. Once it lands on tape, you kind of want that data to be much smaller because it's going to live forever. All right, so if we notice that the 10x of memory here doesn't leave a ton of room for lots of working sets that live in that flash file system, but the tier is very fast. So what we wanted to do is enable data movement across this tier and into the campaign storage tier. So we really want to provide good tools for data management, both for searching for data sets and for allowing the seamless migration of data across these tiers. So a typical user workflow when manipulating their data sets, obviously they want to determine a required input deck before a simulation. These things save initial state. They've got tabular constants They determine the mesh configuration to start, and then obviously any restart information if they're going to be restarting from a checkpoint. So first they need to find the data. Is it in Scratch or hot tier, or is it in our cooler tier campaign, or are they going to be pulling data all the way from the archive? So typically tools that are used now are find and stat, and because we really require the users to drive their data organization. So if they have poor data organization, this can be quite complex and time consuming. Again, we run our simulation, we checkpoint, we migrate data, we run, we checkpoint, and we proceed through repeating those steps until the simulation is complete. The analysis phase is also quite important again, so they're going to potentially smooth or modify some variables of the run, continue running, and then maybe visualize that data. And ultimately, the visualizations get saved to the archive. But like I mentioned, this really requires users to know their data and know the data organization. Otherwise, they're going to waste time searching for data sets. And this doesn't provide a good mechanism for them to sort of annotate their data sets, if you will. If they want to do something like that, they'll have to store information in files. And on these file systems, metadata search can be slow. It's often limited to each file system capability, or if you have parallel search tools or the like. Data movement is done in parallel, although it is slightly complex and it requires a separate cluster. So these are some problems that we want to solve. Okay, and if we take a look to the table on the right, this kind of is a quick snapshot of our open environment, which is significantly smaller than our environment where Crossroads lives. And even in this environment, you can see that we've got close to 700 million files. So definitely data organization is a big problem here. Okay, so solving these challenges, some key technology involved include metadata indexing. So the Grand Unified File Index, or Goofy for short, takes a metadata snapshot of each storage tier in our data center. And what it does is it protects the index in such a way that both administrators and users can access the index simultaneously. We adhere to POSIX permissions of the source storage system. And we sort of solve that by replicating the directory structure and implementing those POSIX permissions on that directory hierarchy. But then instead of replicating any files inside of that directory structure, we put an embedded database, SQLite in this implementation, into the directories that stores information about files and subdirectories that were located there. So very powerful tool. I have linked the paper at the end of this talk. I could spend hours talking about why this is important, but effectively what happens is it enables rapid search across all storage tiers in the data center. Queries that would normally take minutes or hours can be done in mere seconds by both users and administrators alike. The second tool is related to data movement. We want to allow the scheduling of data migration rather than forcing users to log into a separate cluster to execute that data migration. So this is Conduit. It is a set of tools that both enable a CLI and a Slurm scheduler integration. And what it does is it serializes the data movement so that way users don't step on one another when migrating large data sets that may be shared. It can leverage our parallel copy tools, and it also leverages a separate data transfer cluster without having users have to execute commands on a separate system. Okay, our third bullet here is user-defined metadata. So Goofy by itself allowed for user-defined metadata by leveraging extended attributes. Users could query extended attributes through Goofy. However, not all file systems support extended attributes, and not all users are familiar with extended attributes. So what we did is we worked with another local project at LANL, the Data Science Infrastructure Project. And we allowed users to have databases that were stored inside of the source file systems. And we were able to connect Goofy to those source databases to allow for users to insert information about a simulation. Maybe this one was used with this input deck, or this one experienced high energy when these variables were applied. And so they can use the power of Goofy to query both the user-defined metadata and tie it to data sets of interest and give them a powerful query tool to use across both of those sources of data. And lastly, how does computational storage fit in? So you could apply computational storage techniques to systems where the metadata indexing lives to speed up those queries. But we've also done a lot of work in storage system improvements, ZFS and Lustre in particular, where we were able to offload things like compression and data protection transparently to the user inside of the storage system. We've given lots of talks about this, so I encourage you to look up ABOF is certainly one work that we presented at both SDC and other SNIA events. That was a nice collaboration we had done with Idedicom, Aeon Computing, SK Hynix, and NVIDIA. Here at the bottom, you can kind of see a depiction of the Goofy model. I'm not going to go through it here because this is a short talk, but I encourage you to look up the paper and use these diagrams to further understand exactly how Goofy works. Okay, as we move into our second exploration, what a scientist will want to do. So first is a plasma simulation. Okay, so an example of this would be a user wanting to understand how something like magnetic reconnection works. So these are plasma simulations. You sort of flow two plasmas over one another, and I'll quickly preface this with I am not a physicist, but I have talked with a lot of our users, and I kind of understand their thought process when they're working through these workflows. So they want to understand which particles are high, and obviously you have to define what high means when you're doing simulations like this. Okay, so I have data is unordered in quotes here by the application, and what that really means is it's ordered specifically to optimize the writing of the data. It's unordered in a sense of when we want to read the data. It's not ordered in a convenient optimized read layout, and it can't be, right, because we have to have the entire data set and sort it before writing it, which would be very time consuming and slow the application down. When you want to understand which particles are high after you've defined high, how is this done today? I mentioned before that this is done by moving the data. So we're talking about moving petabytes of data back into system memory from a storage system, and then sorting it or building histograms and making visualizations. But we can certainly do better than that. And so these simulations are often file per n processes, so many files that contain a subset of the data set. And one key property to note about these simulations is they're particle based simulations, and they often have a particle ID with values of interest that are tied to that particle ID. So a very record oriented data format. Okay, so if we look at a quick example of a visualization of a particle simulation, every sort of step through the video is a time step of a simulation. So we've got a few time steps here. And we can see here, I believe this is a laser through energizing a plasma. But you can see that the color coding here is effectively building a histogram. They want to understand which ones have high something. And in this case, we're looking at kinetic energy. So the red particles have the highest kinetic energy. And in order to build this visualization, you've had to sort this data on the fields that you want to colorize, right? And so you've got to look at the entire data set to be able to sort it of each time step and then build these videos through time steps. So quite expensive and to build these, but very useful for a simulation scientist to look at the output of their simulation to understand what is going on. So key technology in speeding up this process, let's move away from sorting it after the fact, is the key value API. I've already mentioned that we've got a particle ID and we've got values associated with that particle. So it's a really nice match to record-oriented formats like key value. Obviously, SS tables, LevelDB and RocksDB are highly valuable here. And then secondary indexing in order to support range queries. So this is important because not only do we want we actually don't really care about particles being sorted. What we care about is values associated with particles being sorted. So that's really important. We've done a lot of work with SK Hynix in order to optimize this, and we've seen significant speedups by offloading the entirety of a key value storage system implemented inside of a device, but also looking at just sticking particular functions inside the device, like filtering or compaction. We've also worked with another great partner, AirMetal, in looking at histogram generation. And so when I said we have to define high, oftentimes a scientist won't understand what value will mean high when they're doing the analysis. So they don't have a great starting point to understand the high. They can look at the largest value and the smallest value, but again, that might take a sort. So instead, if we could build space-efficient histograms while the data is being written, we can leverage those to sort of set some bounds before we start running more advanced queries. And like I said, we've seen significant speed ups in the end-to-end workflow using both of these methods. Okay, so I kind of said that the last example was low-hanging fruit because it was particles and particle IDs and values, and there was no really complex mesh oriented behavior with those simulations. But we want to do something more difficult, like tracking a shock wave. When we're out of the plasma simulation regime where we have particles, it gets quite a bit more complex. So if a user wants to track high energy across the edge of a shock wave through time, they may look at prior simulations in 2 dimensions or 3 dimensions to understand past behavior and then get a set of inputs for their current simulation. They may want to leverage our data management tools to go search for the prior simulations. So they'll do a goofy query to say, where was the largest energy at the front of a shock wave early in a simulation or late in a simulation? And these are things that they could have defined using our user-defined metadata scheme. And again, we'll take this same run simulation checkpoint, run, analyze, process, and that will continue to be the same. But what they want to do is they want to understand how this shock waves move through time. So where's the energy high? What does high exactly mean? And what's happening near that high energy? Like I said at the beginning, this is much more complex data organization. So basically the way to think about this data organization is it's columnar in nature. They're basically storing the arrays into the file. And in this case, it's going to be what we refer to as an N-to-1 workload, where N processes are writing all of their data into one file. So it's a shared file regime. And so this is columnar in nature rather than record, because what will happen is every process will store its temperature all in the same section of a file. So you'll have 1 to n processes with 1 to n temperatures inside of a file. And then they'll shift down and they'll write their energies, and they'll shift down and they'll write any other variables of interest. So it's a much different access model than the key value oriented or record oriented format that I described before. And then the last thing to note down here on the bottom is, which makes the data organization more complex, is that in areas of high interest, so you'll see these red or blue areas, the mesh gets refined. So large squares become 4 smaller squares, or 4 smaller squares become 8 smaller squares, for example. And this is because this is where we really care about the data. So we can't fit the entirety of the simulation in memory. So we have to play these tricks by saying, okay, if something's not interesting, let's de-refine there because we don't really care what's happening. But in the really high interesting areas, let's make more mesh blocks. That way we have more areas to explore that are of interest. Okay, so if we look at a wave tracking in 2D example here, oops, we can kind of see that there is phenomena happening against the front of this material. You can kind of see the mesh deforming. And then here, I don't know if it's temperature or energy, but we're tracking a variable by colorizing it and looking at multiple time steps. So how this material is being impacted by this wave going across it. And so you can see that that can be quite complex to, you can see that that can be quite complex to analyze if you have to colorize and build these visualizations for every variable of interest, because it requires large sorts on petabytes of data, right? And then so if we look at a 3D example of tracking a shock wave, again, we're looking at multiple time steps because this is a video, but if we freeze it and look at a single time step, we can see that there's sort of these after effects of an action being occurring. And what the scientists want to do is track sort of the edges of these waves and kind of see how they interact with one another as they disperse, right? And so again, the mesh is deforming in the interesting areas. It's getting smaller, so that way we get, or not getting smaller, getting more refined, so that way we can track the items of interest. And then the areas that may not be of interest anymore have become de-refined. And so these, again, these are very large data sets, petabytes. So this sort becomes very expensive. How can we improve upon that in this columnar case? So key technology, we certainly want to leverage an open ecosystem and existing data analysis tools. We don't want our users to have to learn entirely new data tools or develop new tools that may not be supported in the open source. Okay, so right now, each application, like I said, uses a columnar file format, although it's not always a open file format like Parquet. Some of them are custom with custom readers and writers, and not all of them or any of them provide index capabilities. So we're certainly pushing for something like Apache Parquet. There are already tools that understand Parquet. It's sort of the industry standard. We want to move towards this file format. We also definitely want to leverage pushdown mechanics, something like Substrate to enable computational storage. So if we've got petabyte-sized data sets, we don't want to move that petabyte to filter it. What we'd rather do is filter it as close to where the data is stored as possible. This leads to orders of magnitude less data retrieval. We're certainly interested in alternative pushdown protocols. So block is obviously king, but we also want to see if file protocol may be something interesting at the device level. Certainly object and KV are things we've already demonstrated as being useful. On the histogram work, that can be done at the client side, potentially also done during the analysis phase in the storage system itself. But again, the big goal here is to require significantly fewer resources for our analysis phase. So this is both time and compute resources. We don't want to tie up our supercomputer doing sorts for analysis. Okay, and then finally deciding if maybe middleware is the correct approach. If the middleware histogramming or maybe file conversion or data visualization and finally pushdown. If we need to provide middleware for users to sort of use this stuff transparently, that's definitely something that we can enable. Okay, so if we put it all together, looking at our systems that we'll be deploying now and certainly looking to design and deploy in the future, we may have something like smart memory existing on the system, so we can probably try to leverage that in any way we can. But providing these data management tools, you see them here on the left, directly to compute clients and sort of front-end services. And then sort of disaggregate our storage and our storage servers. That way we can provide more tailored service to the users for a particular IO pattern or IO regime that they want to take advantage of. So things like columnar or key value specific services or just bulk data services that provide high bandwidth. And then have media enclosures that are sort of on the same network and can be exposed either to the data services servers or to the compute clients directly. And this is sort of where both of these tiers are where you can apply computational storage. You can put accelerators inside of the servers, or you can directly have NVMe drives that are computational storage compliant devices inside of your fabric attached enclosures. And then we'll have a much smaller data analysis cluster, so maybe tens of nodes, depending on memory requirements. And then we still have our data transfer cluster out on the right, but data movement is now being scheduled from the compute nodes rather than having direct login and commands being run on our data transfer cluster. And so I thank you for your time. Computational storage has been something very interesting to us over the past few years. It is sort of the forefront of all of our storage research, and we think that it can solve a lot of our data challenges. Thank you.